Okay, so in this tutorial we're going to be going through electrolysis and looking at its uses and how it works and all that sort of stuff. Now, electrolysis can be quite a tricky topic for students because there's quite a few abstract concepts to think about, but it's actually quite a basic thing when you think about it. And it's split up into, or the stuff we're going to be talking about is split up into these bits here. You're splitting up ionic compounds, molten compounds, ionic solutions and discharge rules, using oil rig. We'll come to that a little bit later, and brine and purifying copper. So actually knowing the examples we need to know about for the test. Okay, so let's look at splitting up ionic compounds then. So this is what we mean by an ionic compound then. So an ionic compound, for example, sodium chloride has a giant lattice structure. The ions are in a regular arrangement and they're very tightly bonded together. So things with like ionic compounds have properties such as high melting points, high boiling points, things like that. However, because they have these ions, which are charged, Na+, Cl-, it means that they can dissociate in water quite easily. So they dissolve quite easily. So ionic compounds are made from positive ions, which have lost negative electrons, and negative ions, which have gained negative electrons. So knowing about that loss and gain is important to us. As these ions have opposite charges then, they attract each other strongly to form ionic bonds, which is why the properties of ionic compounds are that they have strong bonds. So in terms of how we split them up, so there are two ways in which we can split them up. First of all, we can melt them, and if we melt them, it'll turn into a liquid. So when you see the little L in brackets on equations, that means that it's liquid, it is molten. Now, as we said, ionic compounds generally have very high melting points. For example, sodium chloride has a melting point of around 800 degrees centigrade, which is very high. Now, obviously, in order to split sodium chloride then up into sodium and chlorine, that's not a very efficient way for us to do it. A far easier way of splitting up these ions is to dissolve them. So in something like water, and you can do that at room temperature, 20 degrees centigrade, and it'll dissolve nicely, they'll dissociate. So let's have a look at how we separate these ions. First of all, let's have a look at this structure we've got here in front of us. We've got a battery or a power source of some sort here. We've got two electrodes here. These are our two electrodes. So this over here is going to be our positive electrode, and this is our negative electrode. The way I remember these is kind of like in your exams you want to get an A+ and not a C-. So A+, this is an anode, A+, and this is a cathode, it's C-. So what the battery does is it pulls electrons off one of those electrodes and pushes them onto the other ones, which means that at the anode then, A+, you get a deficiency of electrons, whereas over here we've got lots of electrons. Okay. So these are the relative charges then of the anode and the cathode respectively. So let's have a look at how we can separate ionic solutions then. So here we've got, I've used the word incorrectly there. It's not a solution. This is a molten ionic compound. Okay, so this is a liquid compound. So what you will get, so we've got our ions separated from each other here. If we put some power into this, then this is what happens. So the ions will dissociate and move to the different electrodes. So the positive ions will move to the cathode and the negative ions will move to the anode. So the things that go to the anode we call anions, and the things that go to the cathode we call cations. So this is a way of splitting up ionic compounds then. So the word that we're looking at is electrolysis. If you split that word up, you get electrolysis. Electro obviously means using electricity, and lysis means splitting. Okay, so splitting with electricity, that's what electrolysis is all about. So splitting up molten sodium chloride, okay, and the molten bit is important here because it is a liquid, it is not a solution. So let's have a look at what happens here then. So we're looking purely at what happens with the chlorine. So the chlorine has gone over now to our anode, which is our positively charged electrode. And the chlorine, if you see this little green blob there, that tells me that there is an excess of electrons in there. Okay, so it's got one spare electron. So at the anode, then it'll lose that, it'll get pulled over, and we get chloride ions losing their electrons and forming neutral chlorine atoms. So obviously the chlorine atoms that are made are covalent compounds, and we get chlorine gas. Now, if ever you're thinking, well, how do I know which ones are diatomic? So for example, chlorine, because it's got a Cl2 here, it's diatomic. And how do you know which ones are which? So what I use to remember this is Hong7, Hong7. So H is hydrogen, and that is diatomic, H2. O is oxygen, which is O2. N is nitrogen, which is N2. And then all of group 7, so chlorine, bromine, fluorine, and iodine, are diatomic as well. So chlorine is a halogen, and so it's diatomic. At the bottom now you can see our half equations. Okay, so we've got this here represents the chlorine, which has got an extra electron. When it goes to the anode, it loses that electron, and we get chlorine left over. Now, obviously, because you can't just get chlorine on its own, that means we're going to have two chlorines together to make chlorine gas. So this is our sort of final half equation here. What's happening at the anode? We've got balanced as well. So 2Cl minus, and then we've got Cl2 plus 2E minus, because those are our electrons, and those are the ones that have been lost. Let's have a look at what's happening. Let's have a look at what's happening at the cathode then. So then we've got sodium, which is going over to the cathode, and if you look, it's kind of missing a hole here. So what that means is that it is deficient in electrons. Now, at the cathode, we got loads of extra electrons there. Those are green blobs. So this is what happens. Those electrons move into there. So the ions become neutral sodium atoms, and they sort of sink to the bottom, and we get solid sodium being formed. remember this is still molten. And this is our half equation here. Na plus E minus, because it's gaining electron at the cathode, gives us sodium. So very quickly, this is what happens. Kind of a summary. What's happening at the anode? We're getting chlorine gas being formed. So you'll see bubbles. That is an observation. That is what you'll see happening there. Chlorine gas being formed. And you'll see solid sodium being formed at the cathode then. So that's with molten sodium chloride. And those are our half equations. Similar example here, lead bromide. Lead is Pb2+, bromine is Br-. So this is what's going to happen. Same sort of thing as before. We get bromine gas being formed and the half equations. If you're a bit like, oh, what's going on here, just pause it at this point and you can have a look through this and figure this out as well. And we get lead being formed at the cathode. And there are our half equations. Okay, so what happens then when the ionic compounds are dissolved in water? Because things become a little bit more complicated. That's because water is H2O, is made up of H plus and OH minus ions. Okay, so H plus and OH minus. We call this group OH minus. That's a hydroxide group. Okay, so it complicates things. So in an ionic solution then, for example, sodium chloride solution, there'll be 4 different types of ions present. 2 of them will be positive and 2 of them will be negative. So what we need to think about is, so this is here we got a solution of sodium chloride. We're going to think, right, what's going to go where? So the anions are going to go to the anode and the cations are going to go to the cathode, as you can see here. So you've got the Cl minus going there and the OH minus to the left, and we've got sodium and hydrogen ions going to the right. But which ions are going to gain those electrons and which are going to get discharged? Okay, so that's what we're going to look at, is which ones will be produced and which ones won't. Right then, so let's have a look at the cathode then. So we've got sodium and hydrogen ions both at the cathode. Which one is going to be produced? So this is what happens. Because hydrogen is less reactive than sodium, it is discharged. So the sodium ions stay in solution. So we get hydrogen gas being formed there. Okay? So bear with me now if you're still a little bit confused, but hydrogen gas is formed because hydrogen is less reactive than sodium. So for this, you need to know our reactivity series of metals. Okay, so that would come in very handy. And there'll be another video posted on the reactivity series of metals you can check out. Let's have a look at the other side then. So we've got OH minus and we've got chlorine minus. Now, if a halogen is present, in which case it is at the moment, we've got chlorine, then the halogen is what is produced. So if the halogen is present, the halogen is produced and is discharged. So we get chlorine gas being formed then. And the OH minus stays behind in the solution. And there's our half equation for that. So again, you can pause at any time if you get a little bit confused. So what about then if we do not have halogen compounds in there? So for example, if here we've got a nitrate groups, NO3-, those are our nitrate groups. So what's going to happen then? Now, if we don't have halogens present, the rule is that the hydroxide ions from the water are discharged, and it's discharged in two forms. So first of all, it's discharged in the form of oxygen gas and water. So we get oxygen gas being produced and water left behind as well. And there's our half equation. So these are our rules then, okay? What's happening at the anode and what's at the cathode. And this is the crux of it. This is what it comes down to. So this is what you need to know. So if ions are halogens at the anode now, the halogen is produced. If the ions are not halogens, however, oxygen is produced and water is left behind. At the cathode, the rules are that if the ions are more reactive than hydrogen, then hydrogen is produced. So for example, there we've got some metals which are more reactive than hydrogen. If the ions, however, are less reactive than hydrogen, then the metal is produced. So this is something that is absolutely key to understand and know, so please pause if necessary. Okay, so here are some example questions. So what you can do at this point is you can pause the video and have a go at some of these questions. There's an example one that's been done for you, potassium chloride. Take note of the state there, so which ones are molten, which ones are in solution, and you've got to identify the ions that are present and what will be produced. Okay, so you can pause, have a go at those, and then have a look at the answers which are coming in a couple of seconds' time. Okay, so here are the answers then. So these are what are going to be produced. I'm not going to go through them all, but what you can do is you can pause it and have a look through to make sure or to find out if you were right. So using the rules that we've looked at, these are the products at the cathode and the anode from the ions that we've got. Okay, so electrolysis then makes a circuit, and that's really important to understand and know. So electrons carry a circuit, an electric current has to be able to flow in order for a circuit to be achieved. So here we've got electrons being carried in electrodes in the wires and ions in the electrolyte. So the current is carried by those two different things, electrons in the electrodes and ions in the electrolyte. Okay, so let's have a look at this oil rig thing we said we were going to come back to earlier on. So we've got oil rig here. Oil rig, if you don't already know, is to do with oxidation and reduction. So oxidation is loss of electrons. I don't know why that keeps popping up. And reduction is gain of electrons. So if over here, for example, we are losing electrons, so we've got chlorine being oxidized. On the right, we've got sodium gaining electrons, and so that is being reduced. So oxidation is loss of electrons, and reduction is gain of electrons. Okay, so some of the uses of electrolysis then. This is what you will be examined on, predominantly. These are the examples they'll look at. So, first of all, it's used to extract reactive metals. For example, aluminium. Now, aluminium is actually very expensive, even though it's very common, and it's one of the most abundant elements in the Earth's crust. It is an expensive thing to produce because it requires electrolysis to extract it from its ore, and electrolysis is not cheap because it takes a heck of a lot of electricity to power electrolysis. So aluminium is extracted from bauxite, which is Al2O3. That's the ore. So this is the ore of aluminium. It's worth knowing. It's also used for the electrolysis of brine to produce these things here. So produce chlorine gas, and these uses you need to know. So you need to know the chlorine is used for disinfectants and things like plastics, and it's used in things like swimming pools as a disinfectant. It's used to produce hydrogen, which is used for ammonia fertilizers and things like margarine even, and sodium hydroxide, which is used for soap and cleaning agents because it's quite a strong alkali. We're going to look a little bit more in depth at some of these things in a minute. And it's used for purifying copper. So the copper we use for wiring needs to be very, very pure, okay? Much more pure than what you get from a blast furnace. So we use electrolysis to convert impure copper to pure copper. We're going to look at how that's done in a minute. So those are some of the main uses you need to know about. So electrolysis of brine then, this is what happens. I'm just going to whiz through this. So we've got sodium chloride solution. We've already talked about this. We've already said what's going to be produced. Brine is just sodium chloride in solution. Okay, so here then we're going to get chlorine gas being produced, which we can use, hydrogen gas, which we can use, and sodium hydroxide solution, which is an alkali, left behind. So all three of those things are useful to industry. So this is a picture which just shows some of the industrial production of chlorine by electrolysis. Okay, purification of copper is the last thing we're going to look at. So on the left, we've got some impure copper. So impure copper contains lots of things that we don't want. And on the right-hand side, we've got pure copper. So we've got an impure copper anode, which is positively charged, and a pure copper cathode. Now that's very important, and we've got that in copper sulfate solution here then. So this is what's going to happen. The copper atoms from the impure copper are oxidized to copper ions. So they will be oxidized, and so those ions become free and are able to move through the solution. They're going to be transported from the anode to the cathode because we've got a positively charged ion going to our cathode. And over there then it's going to be reduced by gaining electrons. Remember, reduction is gaining electrons. And so we're going to get solid, pure copper being produced at the cathode. And because the atoms of the impurities are not transported by this process, the copper that's building up on the anode is extremely pure, which is very important for things like electrical wire, as we've said already. So this is what you kind of see happening. You'll see that over time, the impure copper anode will sort of deteriorate, dissolve away, and break down. We'll get a nice, big, fat lot of pure copper being produced at the cathode. And that's more or less it for electrolysis.